Let's discuss about condensation polymerization or step growth polymerization. In this type of polymerization, there is a repetitive condensation reaction between two bifunctional monomers. The product of each step is again a bifunctional species and the sequence of condensation goes on. As each step produced a distinct functionalized species which is independent of each other, the process is also called as step growth polymerization. In this polycondensation reactions, there is a loss of simple molecules such as water, alcohol, ammonia, and leading to the formation of high molecular mass condensation polymers. Now let me take the example of the bifunctional monomers here. These are hexamethylene diamine and adipic acid. The two join with the elimination of water molecule. You can see the elimination of water molecule, and the product they form, you can see the product formed by them. There is an amide linkage, and see the product. This also can combine with another amino group. This can combine with another acid group. So the product is again a bifunctionalized species. I hope this is clear to everyone. Okay. Now, what is the difference between the step growth reactions and the addition polymerization reactions? It is in step growth, the growing chains react with each other to form even longer chains. But in addition polymerization reactions, only monomers react with the growing chain. Two growing chains cannot join together the way they can in a step growth polymerization. So in step growth polymerization, the chains keep on forming and then they join together to form the polymer. But in addition polymerization, the monomers keep on adding to the growing chain. So this is important. Let's see the example of condensation polymerization reactions, polyamides. The first example is preparation of nylon 6,6. So nylon 6,6 we have already discussed that hexamethylene diamine and adipic acid, they join together at high temperature and high pressure to form nylon 6,6 with the elimination of water molecule. The uses are nylon 6,6 is used in making sheets, bristles for brushes and in textile industry. So you need to know the structure of the monomer, name of the monomer, uses of the monomer, uses of the polymer which is formed, right? So then we come to nylon 6. Nylon 6 is obtained by heating caprolactam with water at high temperature. So this is caprolactam. See the structure 1, 2, 3, 4, 5. This is CONH is the group attached. So from here the cleavage take place, and you can see this is the way you can remember about the polymer. So caprolactam on heating gives nylon 6. You need to know the structure. You need to know the polymer, how polymer is formed, and it is used in the manufacture of tire cords, fabrics and ropes, right? Now we come to the next polymer, next example of condensation polymerization, that is polyesters. How these polyesters are formed? They are formed from dicarboxylic acids and diols. Let's see the first example, decaron or terylene. So this decaron or terylene, this is a diol, ethylene glycol, and this is terphthalic acid. The two join with the elimination of water molecule. When acid and alcohol join together, this results in the formation of ester. So this is the ester linkage. There are a number of such ester linkages. That is why the name polyester. This is known as terylene or decaron, right? This terylene is crease resistant and it is used in blending with cotton. If it is blended with cotton, we get terrycot. If it is blended with wool, we get terry wool. And it is also used as glass reinforcing material in safety helmets. Okay, you can see here the conditions 420 to 460 Kelvin in the presence of the catalyst zinc acetate antimony trioxide catalyst. Okay, now another polyester which is given in the tables at the back of your chapter, let me show you, is glyptal. So glyptal is formed, you can see here, this is glyptal. This is another this polymer which comes under polyesters. It is formed from diol, ethylene glycol, and dicarboxylic acid, phthalic acid. I'll show you here so you can see the preparation of glyptal here. This is ethylene glycol and this is phthalic acid, which is benzene 1,2-dicarboxylic acid, and it polymerized to form the glyptal. It is a network cross-linked polymer and it is used in the manufacture of paints, building materials such as asbestos and cement. See, again in these you need to remember the name of the monomer, the structure of the monomer, and the uses. So this is important regarding the polyamides and polyesters. Let's discuss about phenol formaldehyde polymer. This is obtained by the condensation reaction of phenol with formaldehyde in the presence of an acid or a base catalyst. We can see here, this is phenol, this is formaldehyde, this is an acid or a base catalyst. And first there is a formation of ortho or para hydroxymethyl phenol derivatives. This is ortho hydroxymethyl phenol derivative, also known as ortho-hydroxybenzyl alcohol. Then they react with phenol and they form the compounds having rings joined to each other by CH2 group. This initial product is known as novolac and it is used in paints. This novolac, on heating with formaldehyde, undergoes cross-linking to form the bakelite. The bakelite is used in the making of combs, phonograph records, electrical switches and handles of various utensils. Now the question comes, write the name of the monomers used for getting bakelite and mention 2 uses of bakelite. I hope this is easy. Then we come to the melamine formaldehyde polymer. This polymer is obtained by the condensation polymerization of melamine and formaldehyde. You need to learn the structures. You need to practice a lot because generally students forget these structures, and when they polymerize, they form the melamine polymer, and this is used in the making of unbreakable crockery. Rubber. First we'll discuss about natural rubber. Rubber is a natural polymer. It is an elastomer. It is manufactured from rubber latex. This rubber latex is a colloidal dispersion of rubber in water. The latex is obtained from the bark of the rubber tree. The natural rubber is a linear polymer of isoprene, which is 2-methyl-1,3-butadiene, and this natural rubber is called as cis-1,4-polyisoprene. Let's see the structure of isoprene. It is 2-methyl-1,3-butadiene, and this polymerized to form this cis-1,4-polyisoprene. This cis-polyisoprene consists of various chains which are held together by weak van der Waals interactions, and so it has a coiled structure. It can be stretched like a spring and it exhibits elastic properties. Then we come to the vulcanization of rubber. The natural rubber becomes soft at high temperature and brittle at low temperature. It shows high water absorption capacities. It is soluble in non-polar solvents and is non-resistant to attack by oxidizing agents. In order to improve its properties, the process of vulcanization is carried out. In this process, raw rubber, sulfur, and an appropriate additive is taken. This mixture is heated at a temperature range between 373 Kelvin to 415 Kelvin. On vulcanization, sulfur forms crosslinks at the reactive sites and thus the rubber gets stiffened. You can see the crosslinks which are formed at the reactive sites of the double bond, and so the rubber gets stiffened. In the manufacture of tire rubber, 5% of sulfur is used as a cross-linking agent. Then we come to synthetic rubbers. The synthetic rubbers can be stretched to twice its length, but they return to their original shape and size as soon as the external stretching force is released. Let's study about the synthetic rubbers. Neoprene. Neoprene is also known as polychloroprene, and it is formed by the free radical polymerization of chloroprene. Chloroprene is 2-chloro-1,3-butadiene. This polymerizes to form polychloroprene, also known as neoprene. It has superior resistance to vegetable and mineral oils, and it is used in the manufacture of conveyor belts, gaskets, and hoses. Then we come to Buna-N. Buna-N is formed from 1,3-butadiene and acrylonitrile in the presence of a catalyst, which is peroxide catalyst. This Buna-N is also a copolymer which is formed, and it is resistant to the action of petrol, lubricating oil and organic solvents. So it is used in the making of oil seals and tank linings. Then we have already studied about Buna-S, which is 1,3-butadiene and styrene. This polymer is also known as Buna-S or styrene butadiene rubber. So they all are synthetic rubbers. Let us again see the difference between natural rubber and vulcanized rubber. Please note down this difference. Natural rubber is soft and sticky. Vulcanized rubber is hard and non-sticky. Natural rubber has low tensile strength and vulcanized rubber has high tensile strength. Natural rubber has low elasticity. Vulcanized rubber has high elasticity. Natural rubber can be used over a narrow range of temperature. Vulcanized rubber is used over a wide range of temperature. Natural rubber has low wear and tear resistance, and vulcanized rubber has high wear and tear resistance. The natural rubber is soluble in solvents like ether, carbon tetrachloride, petrol, and vulcanized rubber is insoluble in all the common solvents.